I had a quick question.
Sure.
I don't think anyone's asked it yet, but for 36 and 37 in Dry Lab 1, it's asking for the different isomers, and like we're supposed to count them for dichlorocyclopentane. Uh, but are we only checking isomers that still keep it as cyclopentane, or are we okay to break the break it down to just pentane?
You don't have a choice. And the reason for that is the formula for a cyclic alkane is different than a non-cyclic one.
Gotcha.
Because when you bring the ring around, um,
I know you lose a couple hydrogen, but I wasn't
yeah,
sure if we're supposed to
that
just replace that with a double bond or what. But
no, they don't want you throwing in double bonds. They only want you to, which would be a way to do that, by the way. Very good. Um, yeah, you lose a couple hydrogens when you connect up the ring. And see, that's what messes up the formula for the isomers. So the formula is different because you have two
gotcha.
hydrogens.
All right, cool. Thank you.
Sure. Okay. Okay, whenever we have a double or triple bonded carbon in the hydrocarbon, we call it unsaturated. Alkanes are saturated, means there are only single carbon-carbon bonds. Unsaturated means there are um, usually a mixture of double and single bonded carbons. You can also have no single carbon uh, uh, carbons. For example, if you had that, ethylene, um, but usually you have more than two carbons. And with more than two carbons, typically you have some single carbon-carbon bonds thrown in there. Now, we're not covering triple bonded carbons or triple bonded nitrogen because none of them are in the body. And this is an allied health strand of chemistry, so I'm not going to be covering those. Also, polymers that are non-biological polymers. For example, polyvinyl chloride, uh, PVC would be an example. So those we're going to skip. Okay, so these guys are going to be gone. Now, there's another class of alkenes, or excuse me, back up. Another class of unsaturated hydrocarbons called aromatics, and those contain the benzene ring. And the benzene ring looks like this. And it vibrates back and forth to this. And the way they usually draw it with a circle in the middle of it to indicate this back and forth movement of single to double bonds. And this is a very, very, very stable configuration. That's why it's found in nature a lot. It's also very carcinogenic. It used to be, it was very, very, because it was so stable, it didn't react with very many things. And so they treated it that way. However, they found that because it's so stable, it can actually interfere with the actual transcription of a DNA sequence. It gets put in the spirals and actually messes things up pretty badly. Now it went from, bucket chemistry down to parts per billion. It's very, very carcinogenic. And this is my saying, what's safe today may not be safe tomorrow. Okay. Another point I want to make is everything is in alphabetical order when we're naming, except for some things starting with iso, like isopropyl or isobutyl. Okay, so naming alkenes is basically, we have three parts. One part, the first part is going to always be branching. Let's see, let's do this one here. Okay, so we've got okay, so we need to name it now. Like always, we start with the longest chain that contains a functional group. Okay, in this case, the functional group is going to be a double bond. So it doesn't matter if something's longer, it's got to contain the functional group, no exceptions. Now, it gets more complicated if there are two or more functional groups. You know, which one has the hierarchy to be stronger than the other one, and that gets into some very detailed naming conventions. We're not going to worry about that in this class. It's way out of the scope of this class. Okay, but just in general, we find the functional group, and then the longest chain that contains it will be the backbone. So we've got 1, 2, 3, 4. This way or this way. Either one of those is a 4-carbon chain containing the backbone. All right, so it's going to be a. Now, whenever we have a functional group, we have to say which carbon does it land on. Okay, so we're going to name it via the numbering scheme as we talked about before. If we number from left to right, we're going to get the functional group and the lower numbers. So it's going to be 1-butene. Okay, so this is for double bond, ENE. This is the location of the double bond. Now, you might ask, why isn't it carbon number 2? It's when you count, you have to count the first carbon upon which you encounter the double bond. So as you're counting, the first double bond is going to start at carbon number 1 and go to carbon number 2. So that's why it's number 1. And we've got a branch at carbon number 3. Okay, so with alkanes, we didn't have to name where the functional group was because there wasn't really a functional group. So that's why we left off that number. But from now on, we're going to have to identify what carbon the functional group is on. Okay, does that make sense?
Yes, Professor.
Because we could easily have that. That would be an isomer. Same formula, same number of carbons, same number of hydrogens, but it's not the same molecule at all. So to name that one, that would be in this case, it's going to be 2-butene, 3-methyl. Now later on, we're gonna talk about which is more stable, because when we do reactions, frequently we'll get a mix of alkenes in the product side, and you have to circle which one is more predominant. And there's going to be a rule we're going to come up with that has to do with 2 parts. It's going to be a symmetry part and a number of hydrogens on the terminal carbons part. And we'll get into that when we get to that. Okay. And this one here, we're looking at that would be backbone. And if we number from right to left, we're going to get a lower number. So it's going to be on carbon number 2. And then the branch, the methyl branch is going to be in carbon number 4. And whenever you see this setup, a lot of students will fall into this trap where they go straight across like this, being the longest chain containing a functional group. So you have to be careful. You've got to go every which way to figure out which is the longest. Okay. You can also have alkenes with more than one double bond. You can also have alkenes that are cyclic. So if we look at this guy here, it's going to look like excuse me. Okay, so looking at backbone here, containing the functional group, would be that. So we can name this left to right, right to left. We're going to end up with the same numbering scheme. So let's just go 1, 2, 3, 4. Okay, so again, it's 4 carbons long. And it's got 2 sets of double bonds. So that's going to be a diene. That's a di there. And it's at positions 1 and 3. So this has to correspond with the number there. So we have di, meaning we have to have 2 numbers here. Could be the same number. It could be a 1, 1, not with a double bond, but as long as the di and the number over here correspond, you're okay. But if you say try here, you're going to have 3 numbers on the front over here. Okay, and then we have a couple of branches. We have a couple of dimethyls at positions 2 and 3. So it's 2, 3 dimethyl, 1, 3 butadiene. And then we can also have cyclic alkenes as well. Now they're a little trickier to number because you can have various combinations. And remember, when you're numbering double bonds, you count the first one. Like in this case here, we're numbering clockwise. So that would be carbon number 1 there. Carbon number 3. So you could start down here, labeling going counterclockwise as 1, 2, 3, 4. What you do is you do both of those and see which one gives a more favorable numbering. And when I say favorable, I'm talking about the least number. Okay, and this just takes a whole bunch of practice, like all the other numbering. Now, last week we talked about cis and trans isomers, because we had a rigidity whenever we had a cyclic alkane. Now, double bonds are rigid. Therefore, you can have cis, trans isomers, possible. Possible, keyword. Sometimes you do, sometimes you don't. Just depends on what's going on with where the double bond is located. There's a couple of variables there. But you should definitely, as soon as you get rigidity, like with the cyclic alkanes, stop and say, are cis-trans isomers possible? And if it is, then you need to draw them as such and label them as such. Now, if you look at the difference between these two 4-carbon alkenes, big difference in melting points and boiling points. Molar masses are exactly the same, but their melting points and boiling points are not. That has to do with how they lay together in a solution. Depending on whether it's cis or trans, one can get closer than the other. The ones that can get closer are the cis's, because that's melting point and boiling point are higher, so they're more sticky to one another. They cling to one another more. In the situation with trans, they can't get as close, hence their melting and boiling point is going to be not as high. Okay. They're basically almost the same as alkanes. They're nonpolar, can't dissolve in water. They float on water. Gasoline-like odors, because a lot of gasoline has benzene and octane in it, which are similar to the alkane versions. They have a lot of benzene in gasoline. A lot of benzene. Okay. As you can see, there's a definite trend going here. As you add carbons, all you're doing is making the molar mass increase. So if this was molar mass, as it increases, so does the boiling point, melting point, etc. Same with alkanes. Okay, so that's naming, and that's some physical properties. Now, what gets interesting are the reactions. This is a very important statement here. Alkenes are quite chemically reactive, and it has to do with this double bond. One of the bonds is very stable, and the other one is not. The bond that is stable called a sigma bond. The bond that's unstable is called a pi bond. The electrons in the pi bond are the unstable ones. The electrons in the sigma bond are very stable. That's why this goes from unstable to stable. Now, some courses go into great detail on what this looks like at the atomic level. We are not going there. All you need to know is the reason why the pi bond, this double bond, the pi electrons are unstable. That's what's driving this reaction to become sigma bonds only. Okay, so this is also called an addition reaction, because we're adding across the double bond. Oh, it says it right there. Okay, so we have a binary compound. And it's going to attach across there. Now there's two types of binary compounds. There are homogeneous and heterogeneous. Okay. Homogeneous like Cl2 or H2. Those would be examples of homogeneous. Notice how I wrote water. Water's got an H and an OH in it. And that's how it's going to be seen in organic chemistry as an H attached to an OH. Okay. So on your diagram chart that I showed you last time, this is at the top. When we add homogeneous, we're going to create, it's going to add across the double bond. Notice here, we need a platinum catalyst. Okay. Whenever you add a heterogeneic additive, you're going to get a mix. When you're adding, so this is going to be a mix as well. This is heterogeneous. Notice the water has to have a acid. Frequently, strong acids in organic chemistry are usually H2SO4 or phosphoric acid. Like when we make aspirin, we're going to be using phosphoric acid. Okay, so now this is important, this mix, because once we have a mix, then we have to determine which ones are stable and which ones are less stable. And when you have no mix, you don't have to worry about that. Okay, so there's 4 situations I'm going to talk about here. Okay, in this situation, since this is a homogeneous mix here, we are going to take basically this guy, and we're going to lay it right up here. And when you do that, this bond here goes there. This bond here goes there. So what we end up with is that. Again, sigma bond. So the pi bond is the one that's breaking up because it's the unstable one. Same thing with H2. And any of these catalysts can be used, not always platinum. It could be any of these. I usually just say a platinum catalyst is because it's always the popular one, but you can use other ones as well. Okay, so whenever we hydrogenate an alkene, it's the same as what we did up here, up above. We're adding the bromine across the double bond. We're adding H2 across the double bond, exactly the same way. So you're going to have okay. And then we're going to have this go there, this go there. So we're going to end up with the same thing again. Sigma bond. Okay, so those are pretty straightforward. This reaction is particularly important in the food industry. Actually in the pesticide industry as well. But typically vegetable oils, not typically, 99.9% of the time, vegetable oils are polyunsaturated or unsaturated, meaning it contains double bonds. When we hydrogenate that oil, we convert the double bonds to single bonds. But usually not all the single bonds, to some single bonds. Plus, okay, so this is a big deal. If the polyunsaturated vegetable oil is not totally converted to single bonds, you have leftover double bonds, and the leftover double bonds convert to trans because polyunsaturated fats or oils are all cis. When we convert them, they convert to trans. That's why Crisco company, which basically is a substitute for lard in baking, almost went out of business because what it would do, it would take vegetable oil, partially hydrogenate it to get it to act like lard. But what we ended up with, it was a whole bunch of trans fats. And when we found out trans fats were bad for you, the company almost went out of business. So what it does now, it just takes a mixture of non-processed vegetable oils to blend them together to get the same consistency. So Costco now is fine. It doesn't have a ton of trans fats in it like it used to, but it was a major economic blow to that company. Okay, so when we have a mixture, when we are looking at heterogeneic additions to that double bond, we get a mixture most of the time. Sometimes you don't, sometimes you do. Okay, if we get a mixture of different compounds, we then have to figure out which is most stable, and that's the one we're going to circle. Now, there are two rules you're going to go by. One is Markovnikov's rule, which says you're looking at terminal hydrogens. We have a total of 5. Five terminal hydrogens. Okay, the compound that has the most terminal hydrogens is more stable. They coined this phrase, the rich get richer, but I don't know. Okay, so that Markovnikov's rule is number 1. Number 2 is symmetry. Nature loves symmetric molecules more than unsymmetric molecules. So, for example, if we are looking at okay, we have a 1,2-butadiene and 2,3-butadiene, which is more stable. Okay, so first of all, which is more symmetrical, the 2,3 or the 1,2-butadiene? Just eyeball it. That one. Okay.
2, 3.
More. I'm sorry, what?
Yeah, the 2, 3. Yeah, I was
Oh, okay. Yeah, exactly.
skittishly answering.
Now, most books don't talk about symmetry, but symmetry comes into play a lot in organic chemistry in determining the stability of the resulting product. Okay, the other way is to use Markovnikov's rule. Okay, we've got 3 hydrogens there, 2 hydrogens there, 3 hydrogens there, 3 hydrogens there. So 5, 6 total. 6 wins. So you have symmetry and Markovnikov. So the bottom one, the 2,3-butadiene, is definitely going to be more stable than the 1,2-butadiene. Hence, this is the one you're going to circle. And sometimes they'll ask you why, sometimes they don't. But the main thing is, whenever there's a mixture, circle the one that is most stable. Now, you're going to get a mix of both of them. There's a statistical deal like how much more stable is the 2,3 over the 1,2. It just depends. But you'll end up with more of one than the other. It could be like a 60-40, something like that. Now, the problem is, if the goal of the reaction is to obtain a 1,2-butadiene, then you've got to figure out a way to differentiate between these two chemically. And then that's going to be your purification process. One way is crystallization, because their melting points are going to be different. Could be an instrumentation process, whatever. Like we create aspirin. We're going to use a recrystallization process to purify the aspirin. Okay, so there's 2 stability considerations, symmetry and Markovnikov, okay? So when we go back up here, and I mentioned way up here, mix and mix. Always look at the results. Now, you may not have a mixture, but you may have a mixture. And when I say mixture, I'm talking about different products. Okay, so let's now. All right. And again, this is heterogeneric now. Whenever we add a heterogeneric additive, expect a mix. Not all the time, but again, expect a mix. So for example, let's look at this guy down here. Okay. So we're taking a propene plus HCl. What do we get? Well, the HCl is going to be here and here. Statistically, 50% of the time, it's going to be one way, 50% of the time, it's going to be the other way. Hence, mixture. So what's going to end up is going to look like this. So the H is going to go, let's see, let's do this a little differently. Let's do colors here. Blue. So you've got a mixture. I'm going to deal with a mixture. Okay, what we need to do is figure out which is more stable. So symmetry, which is more symmetrical, left or right? And don't forget there are H's around here. There's an H there, H there, H there. So which is more symmetrical, left or right? And for you shy ones out there, it's the right one. So far the right one is more stable. What about according to Markovnikov? Well, we've got 3 there, 3 there. So that's 6 hydrogens. We've got 2 here and 3 there, so that's 5 hydrogens. So Markovnikov says also the right one is going to be more stable. We circle it. Okay, so that process, always do the 2 processes, symmetry and Markovnikov. Sometimes Markovnikov will be, the numbers will be equal. Then the only thing you got to go on is symmetry. And again, this is a gut level feeling. There are no rules on symmetry. I like to say, which one looks more balanced, the left or the right one? Okay, are there any questions about that stability rule when there's a mixture? Okay. All right, so anytime we add a heterogeneric additive across a double bond, look for a mixture. Okay, and this one requires a catalyst. Now, the next heterogeneic additive is going to be water. That's going to be acidic water. And it's called hydration. So there's hydrolysis and hydration. Hydration is the addition of water. So this is how to form an alcohol. An alcohol has got an OH group. And the OH group comes from the OH on the water. So we add that across. Again, there's going to be a mixture. So if we look at, let's take propene again. Plus water. Acidic environment. It's going to add one of two ways. So we're going to end up with and for the same logic we used up above here, in Markovnikovs, we've got 3 and 3, so that's,
Would it be the left?
yes, yeah, exactly the same reason as with the chlorine. Yeah, it's balanced, it's symmetrical, so the symmetry wins out. We're looking at Markovnikov's hydrogens, that's 5. So Markovnikov says it's more symmetrical as well. So
Can you go back really quick, just like 2 seconds? Sorry, I just want to finish
over
drawing.
here,
Sorry, me. Just I'm almost done. Sorry. Okay, thank you.
you're welcome. Okay, so those are, and let me add one other thing. When we get into the next chapter on alcohols, all these reactions are two-way, forwards and backwards. The forward reaction is much more stable and favored
I
than
get
the
like half of it.
reverse
so far.
reaction. I'm sorry, what?
Doesn't explain as well. I do ask questions. Just fucking read it. I just have going right now. Why college so hard? No, why did I gotta take the hard class?
Jason, can you mute yourself, please?
Sorry.
Thank you.
Okay, you should have a side email chat. Okay, so whenever we eliminate the double bond to a single bond, that's favored. And you'll give off energy. And we can go the opposite way, but we have to add energy to go the opposite way. So when we get into the next chapter, we're going to see that and the energy is going to be in terms of heat. So this energy is in the form of heat. Okay. So all reactions in nature are reversible. It's just that one is favored over the other. And the favored one gives off energy. The unfavorable one requires energy to work. So to create a double bond, we start with usually an alcohol. And so basically we're going to reverse this guy here. So we're taking an alcohol with heat. And don't worry about writing this down because we're going to cover it extensively in the next chapter. But my point in this is that reactions are reversible. One is more favored than the other. Okay, so aliphatic compounds have no benzene in it. Aromatic compounds have benzene or a structural relative. In other words, fused rings. In other words, fused rings like that. And that you'll run into those actually quite a bit when you look at a Browning reaction and cooking. When you burn wood, you create a lot of very, they're called polyphenols, and those are very unhealthy for you. So eating barbecue every day of the week is not a good idea. Okay, so we're not going into this atomic level stuff. So as I was stating at the beginning of this lecture, we've got this combination of single double bonds in a ring, and it's a six-membered ring. And what happens is they usually draw it like this. So okay, and because of that, there's only one hydrogen here rather than two.
Your toast is ready.
Okay. Where's the charger?
It's in there,
In here?
right there.
And the cube?
It should be in a little pocket.
Oh, you didn't take it out?
Okay, now. Ben-
Okay, I'm coming.
Miss Gia, your microphone, please.
Sorry.
When we talk about benzene naming can be kind of tricky because it depends on whether the benzene product is the base, the main base, or a branch. And unfortunately, when it's a branch, the name is different. Okay, if it's the main molecule like bromobenzene or chlorobenzene, benzene is going to be in the name. However, and these are some common, instead of calling this methyl benzene, they call it toluene. Instead of hydroxybenzene, they call it phenol. Instead of aminobenzene, it's aniline. Instead of, well, benzoic acid is actually kind of consistent with the base of benzene. So aminobenzene, it's called aniline. Now we're going to be getting to this next chapter. Toluene goes back to the last chapter, really. Okay, so if the benzene is the base, these are the names we're going to use. And these are the common ones. So you need to know this one, and for our unit 1, you need to know that one. Okay. Now, this is where.
Wait, sorry, Professor. Did you just check all four? Just confirming. Just
No, I said for unit 1, you need to know
Oh.
toluene and phenol.
totally okay.
Aniline is going to be another chapter. I mean, another unit. Same with benzoic acid.
Got the first two. Okay.
This is going to be unit 3. This is going to be unit 4. Okay, now this is the tricky part. When benzene is a branch, it's not called benzene, it's called phenyl. Now, it's rarely written like this. If on a test, I would have it look like this. I would not do the formula. Okay, so same old backbone. Now, this backbone does not contain any functional groups. The phenyl is considered a aromatic branch. It's not a functional group. So then we're going to go back to what we did on the last chapter on naming in terms of backbone and minimizing the branching number. So this would be so it doesn't matter if we go left or right, we still end up with the fourth carbon in the middle. And in this case, it's phenyl. 7 carbons, it's heptane. You can have multiple phenyl branching, as we do here. This is cyclobutane, very unstable hydrocarbon. And we have branching at carbon number 1 twice. So the di, 2 numbers. So that's something you need to keep in mind. Is it a branch or is it the main molecule? Branch is phenyl, main molecule benzene. Now this is kind of old world naming. I'm talking about alchemy kind of naming. There are 2 ways to name this benzene product here. Okay, they're both dibromo. One is 1,2-dibromo. Benzene, or ortho dibromo benzene. And frequently on tests, I'll say name this 2 ways, and these would be the 2 ways you name it: 1,2-dibromo or ortho dibromo benzene. Meta era. Okay. The way I remember these, I think of the word or is a little word. Hence, they have a little distance here, so they're together. Para, think of parasailing. Parasailing is with a plane-like device. Okay, you have wings opposing one another. And meta is in the middle. That's the way I remember these. Okay, you can only do this if there are 2 branches off the benzene. If there are 3, then we revert back to the numbering. And in this case, there are 3, but the base, instead of benzene, the base is going to be benzoic acid. Okay. Aromatics are very consistent with alkanes and alkenes, nonpolar, insoluble in water, hydrophobic. Okay. Whenever you refine crude oil, you end up with a mixture of aromatics and aliphatic compounds. That's why gasoline has a whole bunch of benzene in it, a bunch of toluene in it. Back in the days of when I was in high school, I used to drive a very large Chevy station wagon, 59 Bel Air station wagon. And it got about 3 miles per gallon, had a big giant V8 in it, and I was always running out of gas because I worked at the officers club as a busboy making $1.20 an hour, and I just fueling that monster was awful. So excuse me. So I frequently was siphoning gas out of my parents' car. And I'd always end up with a mouthful of gasoline, more times than I like to mention. And, you know, by today's standard, that was really very, very unhealthy. One, I got into my lungs, which of course, benzene got immediately absorbed, or it's in the mucous membrane of my mouth and trachea and esophageal. It was just very, very unhealthy. But anyway, those were the days. It was in the mid 60s when I was in high school. Let's see. Aromatic rings are very, very, very stable. And in terms of, even though it's got a double bond in it, it doesn't react like an alkene. Because it's a single, double, single, double, single, double. And that's where the stability comes in, is that structure is particularly stable because what happens is there's something called resonance going on that stabilizes that pi electron. Remember, the pi electron is one that's unstable. Okay, so this is the guy you need to know. This is the guy you need to know for Unit 1. We're going to talk about phenol a lot in the next chapter. Aromatic compounds are very, very biochemically prevalent. You see them in terms of this is phenylalanine as an amino acid. We find it in hormones. We find it in drugs. We find it in neurotransmitters. They're just all over the place. Very, very common. Now, the last thing I want to talk about is polycyclic aromatics. And that's when we have multiple benzene rings fused together. And these take on similar reactions and properties of benzene. And these guys are the two that are in unburned wood, that black stuff at the bottom of your pan when you cook on an open campfire or in your chimney. And this is how chimney sweeps were found to have bladder cancer higher than the national average, is that they were exposed to these two chemicals, the benzopyrene and dibenzoanthracene. Both of them are very carcinogenic. For the same reason, benzene is carcinogenic. Okay, so that's our chapter on alkenes. Now, the big thing in this chapter are reactions, because the reactions are much more varied than the reactions of alkanes. Because alkanes, you only had two reactions. Here we've got, go back up to that chart. Where's the chart? Okay, so for this chapter, we've got 4 reactions. So now we have a total of 6 reactions. And if you count all these reverse reactions, we now have 10 reactions and all the complexities. So the emphasis in this chapter, in fact, in all the chapters, is going to be intermolecular forces, naming reactions. Every single test will have those component parts, except for the last test. The last test is pure biochemistry. And that's, in fact, that test is going to be open book. Okay, open notes, open book, whatever you like. So this is the complexity, what you're looking at here in this chapter. So what I want to do now is just go through a bunch of examples.
Any news on the lab manual, Professor?
Not a bit. I don't understand. I mean, this is, I can't think of an easier publishing process to go through. Is to take a digital copy of what I gave him and make 100 copies, 200 copies. How much simpler can it be?
Really don't know, Professor. I really don't know. I've had to do
No, I know,
like that, and it's ridiculous. I don't know.
Yeah. it
And they
is-
won't even call us back.
No, well, I sent it all on an email. And I copied the department chairman on it as well, and he just says, give them digital copies until the bookstore comes in. And if we go much further, I'm just gonna say, I'm gonna give you the whole thing.
Like
Right.
the PDF.
I didn't quote unquote give it to you, but,
You didn't. We found it on the internet somehow.
oh, really?
Yeah, you know.
Cool. I mean, not cool, but
Yeah,
Is
yeah.
there a
You know what I
link?
mean. You know what I mean.
yeah, could you share that with the class, please?
No, no, no. That was me joking. I was saying like if you do share it, that's our. That's
Oh,
our
I see what you mean. Yeah, 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 yeah. Yeah. Somehow it'll just appear. Don't know how. Yes, actually, if you did a PDF search, it may well be there. So, and if any of you do that, let me know. I'm curious. Because I know frequently the textbooks are in a PDF file, usually a back version or two, and grab those because their chemistry doesn't change that much from version to version. They have different pictures and different examples. That's about it. Okay, so let's do some examples here. All right. Okay, so I've got this guy here, and I throw it in acidic water. What do I get? Okay, well, this is going to be addition heterogeneous, so expect mixture, and we're going to end up with, that's the backbone. So it's a 1, 2, 3, 4. So it's a butene. And it's going to be a 1 butene, and we're going to have a methyl group on carbon number 2. Okay, so we're going to throw in some water because it's heterogeneic additive. It's going to add across carbons 1 and 2. So the first time the OH is going to add here. And then the second time, the OH is going to be on carbon number 2. Okay, so that's going to be the mixture. And we have to name them. So this is going to be a 4-carbon backbone on both of these. Now these are alcohols. Now we're going to get into alcohols on Wednesday, but the functional group name for an alcohol is OL. So this is going to be a butanol. And it's going to be 1 butanol. And we have a methyl group on carbon 2. And this is going to be two butanol and a methyl group on carbon number 2. Okay, next question is which one's more stable? So we have symmetry question.
The right looks more symmetrical.
I think so too. And we have Markovnikov. Okay, so the right one is the OH group is more in the middle, so it's more balanced. Now, when we get into the next chapter on alcohols, that oxygen is very, very electronegative, meaning it's really going to be very polar. So on the right one, the polarity of that molecule is more balanced. It's more in the middle. Markovnikov, we've got 3 hydrogens, 3 hydrogens, 2 hydrogens. It looks like it's 8 hydrogens. Here we've got 3, 3, 3, so that's 9 hydrogens. So Markovnikov is also favored. So, okay, so that's a complete reaction. So I gave you reactants and the conditions. Conditions are water plus H2SO4. And then you predict the products. Now, we can also, I'll give you a product and I'll say, how do you make it? And the reverse. So let's try. Are there any questions about this before I go on?
I just have a clarification question in regards to I'm gonna butcher the name, the Markov rule. So we're just counting all the hydrogen, or are we?
No,
No,
terminal.
just terminal hydrogen. Okay, just making
Yeah.
sure.
One's on the end. Yeah.
Gotcha. Okay, thank you.
Okay, so let's do let's see. Okay, so how would I make that? So what I want to do is I want to pull up the reaction chart. I showed you that once before. Where is the reaction chart? All right. I'm sorry about this. I should have this already loaded here. Okay. So let's use this flow chart on this here. First of all, what is it? Okay. Is it an alkane or an alkene? Well, it's an alkane that's been chlorinated or halogenated. Okay. That's this guy here or this guy. And how did we get here? Well, we got here from either an alkane or an alkene. So there's two ways to make this. Does everyone see how we ended up? So there's two haloalkanes on the flow chart. We can start with an alkane halogenated, or we can start with an alkene and halogenated.
It would be how keen, like you said.
Well, you can make it either way. So
Oh.
in the test, if you start with an alkane, that would be fine. Start with an alkene, that would be fine too. My point is, how do you use this chart? Okay, that's the main focus of what we're doing right now. How do you use the chart? You're getting this chart on the tests. You don't have to memorize this. Okay, so let's look at this guy now. Okay, we've got, let's just go the alkene route since we're doing alkenes right now. All right, so there are actually, there's two ways to do this on alkenes. One way gives you multiple branches. The other gives you a single one. So we're going to use the HCl route because we only want a single chlorine. And remember, the chlorine comes from a double bond. So let's see, where were we here? Okay. All right, so there's a couple different ways, a couple different answers for this problem. If we looked at, if we had a double bond here, we're going to get a mixture of the Cl here and the Cl there. One of them is going to be in the correct location. So that would be an okay solution. Because of the mixture, one of them would be what we want. Does that make sense?
Yes.
If the double bond was there, we get chlorine there and a chlorine there. And one of them is what we want also. So that would be an acceptable start. Either one would be correct. And of course, the problem is both of them create a mixture, and then you've got to figure out how to purify it. But as far as a test question goes, how do you make that? That would be the way to do it. Okay, does everyone see how I get a mixture here of the chlorine being here and here? Again, it's the chlorine will appear on either side of the double bond. So basically, it's kind of like, think of the double bond, either side of that chlorine will end up with a chlorine on that site. So then what you need to do is then and clean this up. We need to name this. This would be a 1, 2, 3, 4, 5. So it'd be a pentene, and this would be a 2-pentene. This would be a 1-pentene, and this would be a 2-chloro-pentane. So that's how you'd receive full credit in this. Name, name, or name and conditions. And lastly, the other one is using this up here. You'd end up with heat. And this would be just pentane. The problem with this one is the location of the chlorine is going to be sort of random. You know, you can have one chlorine, so this would be the worst way to go. Just because of the complex mixture. And these two would be the cleanest. In fact, well, you're going to get a similar mixture between these two, but one of them would probably be easier to clean up afterwards. And then as a chemist, and then you look at purification methods and differences in melting points and differences in polarity, you know, all that stuff. And then you think of ways that would differentiate between those properties. Okay, does this make sense? Okay, so this is a synthesis problem. I'll give you what and tell me how to make it. Now, the more we go in this class, the more complex this flow chart is going to become. Because we haven't touched those alcohols. Also, I didn't talk at all about also burning alkenes. With a spark, alkenes burn quite nicely. For example, gasoline. A lot of benzene in it, toluene in it. Burns quite nicely. Okay, so are there any questions about this last problem?
Will you move the screen downward so I can finish copying?
That better?
Yes.
Now, today in lab, we're doing, or this week in lab, you're going to do the dry lab on alkenes, and you should start working on the beginning part of dry lab 3 on alcohols. And then don't forget, can I get off
You
this?
mean dry lab 2?
Huh?
You mean dry lab 2, Professor? We've done 0 and 1 for submission, and 2 is due on the 11th.
Yeah, but I'm saying dry lab 2 is on alkenes. And then
Yes, sir. Okay, sorry.
and then the next one is going to be on alcohols. Okay, I want to zoom over to now, I would encourage you to go to Files, Unit 1, Worksheets, and start looking at some of these additional worksheets. For example, here's an alkene one. Okay, naming products. Some of these are going to give mixtures, some not. For example, this one is going to be a mixture because it's a heterogeneic, heterogeneic, heterogeneic. So the 11 through 14, for example, you're going to get a mix. Make sure you circle the one that's most stable. The ones above that are all homogeneous, so you're not going to get a mixture on those. And then here's some practice naming. And these are all eligible test questions also. And this group here, the NO2, is called a nitro group. So that would be, you know, a tri. Now this would be a benzene base. So this would be a couple different ways to number, but one way would be 1-methyl trinitro 2,4,6 trinitro benzene. Okay, anyway, so there's some more additional worksheets besides that one. These I would encourage you to do because one, there's line drawings, and two, I think these are more focused on the chemistry part. The dry labs have some kind of generic concepts involved, which are good for overall, but specifically for reactions and naming, these worksheets are, that's all they do. Okay, so that's what I wanted to cover today. Okay, I'm looking at the chats here. I can give you more time on dry lab too. It's up to you whether you want to attend on dry lab days. I don't take attendance, as you know. You can work in groups also. If you want to work in groups outside the lab, that works fine. In fact, I'm going to do that right now. Let's see here. Also, I want to mention make sure you watch this video of how to do a pre-lab write-up. These are required before you can start a wet lab. They're very straightforward. They're kind of a pain to do, but they're not hard. Everyone in the department except for 305 and Chem 305 and 300 don't have to do these extensive write-ups, but any other chemistry, you've got to do these extensive write-ups. 309 does the same thing. We share a lot of common 400, 401, 412. Anyway, they all require a pretty extensive write-up where you're handwriting the procedure and all that. Okay. All right, so that's it for today. Are there any questions about? Yes, I am going to be posting today's Zoom. I will that.